Hello, everyone. Welcome, and thanks for joining us for the Secure Boot webinar presented by wolfSSL Security Engineer Daniele Lacamera.
Thanks, everyone, for joining this webinar on Secure Boot organized by wolfSSL. And first of all, we would like to introduce the scope of this presentation. So what Secure Boot is and what kind of problems it solves. We recognize a trend on the market where more and more devices are getting connected to the internet. Where are we standing today as embedded system designers, developers, or system integrators? Are we currently following the correct standards and technologies to implement security in connected systems? And are we familiar with vulnerability management and those practices that are popular in the information technology world? In other words, are our connected system secure, or is security still the S in IoT, as the old joke stated? Let's have a look first at embedded Linux systems. The security strategy here derives directly from other markets where Linux is very popular. So security updates are made easier because of package management systems, and also system updates rely on bootloaders that often implement advanced features, device drivers even. The Linux kernel has the advantage of being compiled as a position-independent executable, so it can be easily remapped in memory by the bootloader at boot. Updates are easy, as we said. Security by design is supported by wolfSSL, which is distributed with major Linux distributions, and also in embedded Linux distributions such as OpenWRT or OpenEmbedded Yocto systems. And our contribution in the Secure Boot and Linux comes into many forms, of course. In particular, we recently added Wolf TPM support to Barebox to enable hardware TPM modules to be used for Secure Boot on those kind of systems. The discussion changes completely when we talk about microcontroller-based embedded devices, because developing secure solutions on microcontroller architectures poses different kind of issues. Most embedded systems run using a flat memory model, which means that every task or procedure can basically access any resource that's mapped in memory, which makes the environment pretty unsafe. In such an unsafe environment, vulnerability are particularly difficult to tackle because every software component that has a vulnerability may compromise the entire system. Microcontrollers are also equipped with connectivity technologies using different standards. So it's difficult to understand actually how we could uniform remote updates on these systems. And there is no standards on remote updates besides very recent attempts that we'll analyze in this talk. There has been no standard, neither real or de facto, for the industry to implement remote firmware updates. At wolfSSL, we are constantly busy bringing secure connectivity to embedded devices of any size. So what we do is we provide the same open standards that are used in IT infrastructure for microcontroller-based systems as well. wolfSSL adapts to any type of transport layer, which can be TCP/IP, like in most cases, or even a custom data link. And this is done to provide TLS connectivity over basically any channel. We also provide connectivity protocols that are typical components of modern IoT solutions. Wolf MQTT is our MQTT client, which provides security by default and supports up to MQTT version 5.0. wolfSSH is a library that provides SSH, SCP, SFTP support to embedded systems of any size. And let's say in the common effort of delivering a secure solution, from our side, we are happy to provide any IoT manufacturer with the latest standards. On the other side, we expect that our customer always ensure that the latest version is delivered. If on both sides things go right, the security is actually delivered. But this is only for the release day, as we will see soon. Using the latest version of TLS in a product that's being developed today ensures for sure a longer life of for the product, and increases the level of security significantly, because TLS 1.3 is the latest standard for security cipher suites and a secure communication between two connected endpoints, and it's been released last August, and we were among the first to implement it in our library. And reducing the attack surface on the day of delivery, but we know that vulnerabilities are discovered on a regular basis. So security experts work around the clock to fix known issues and promptly release a fix. But what happens when your device becomes vulnerable and it's already deployed on the field? Are we ready to react to fix defects and bugs in the entire software stack? But it's also important, do we have a strategy for vulnerability management and security updates, like it happens on other markets, which is often a weak point in IoT embedded devices? For this reason, let's say, firmware update becomes a kind of requirement. It becomes actually a requirement. And we were looking to build a secure boot solution which complies to the current open standards. A group within IETF, the IETF suite working group, I've been working on an internet draft to define the guidelines for firmware upgrades, for firmware update architecture. This architecture is designed to scale down to very small resource-constrained device, such as low-power connected nodes based on Cortex M0, for instance. This draft has a few recommendations on the components that are used for the remote updates. The first recommendation is that there must be a minimalist bootloader, which only contains flash support, cryptographic primitives, and it says optionally a recovery mechanism. So the bootloader is, as we said, just one component, because the remote firmware transfer, according to this specification, is implemented in the application, because this document recognizes that it's often a very specific connectivity technology in use in this IoT projects. So it's the application that has to take care of transferring the update. The bootloader, on the other hand, must provide a secure mechanism that's based on asymmetric cryptography to verify the authenticity and integrity of the firmware. And this is the main feature that has to be implemented at bootloader level. These are some additional requirements that we assembled together in order to achieve a solid, safe, and high portable design and implementation. So we have a strong focus on portability across all 32-bit microcontrollers. We use SHA-2, a digest, to verify the integrity of the system. We use, as recommended, public key-based authentication to verify the authenticity of the firmware before booting. We aim for a small footprint to run on the smallest devices on the market. We provide memory safety. We, in fact, disallow any kind of dynamic memory allocation within the bootloader to reduce the attack surface based on memory displacement and buffer overflows. Interrupts are disabled at all times in order to be able to predict the flow from the power on to when the application is actually staged. CPU clock settings should be optimized to speed up the authentication step. And we do offer a reliable firmware update mechanism, which is independent from the update transport mechanism used, and is able to replace a failed update, which was authenticated but didn't produce a stable system, back into its working state before the update by putting back the original image in place. So I will now introduce you a little bit further to wolfSSL Secure Bootloader, which we have recently developed to provide secure firmware updates for all 32-bit microcontrollers. As we said, portability has been, of course, one of our primary concerns. The first version of the bootloader has been initially released with ARM support for Cortex-M. We recently separated the architecture-specific code in order to be able to accommodate a RISC-V implementation. MIPS 32 support is in the roadmap, and more details will be available soon about this architecture. And but wolfBoot can be ported to virtually any 32-bit microcontroller, and it's capable of staging any existing bare metal firmware or real-time OS-based system. A firmware authentication is done at boot time using open standard public key cryptography. So elliptic curve-based digital signature authentication, which is provided by wolfCrypt. No secure elements are required by default to run in the simplest mode, although wolfBoot can be integrated with some platform-specific trusted elements or hardware encryption modules. And of course, the source code and secure firmware update examples are all available on GitHub, and wolfBoot and its examples are released under the terms of GPL version 2. The secure boot can be also chained to other bootloaders to add specific features. For instance, on some architectures, like on NXP Kinetis, there is often a bootloader which is provided in immutable ROM flash. On this platform, for instance, we recommend to chain load wolfBoot as a second stage bootloader in order to add cryptography-based verification of the authenticity of the updates. And of course, other combinations can be possible, and wolfBoot can be chained at any stage of the boot chain. wolfBoot relies on a multi-slot partitioning of the programming flash, but can also be compiled to map the update partition on an external device, such as an external SPI flash memory. This is a panoramic of the components and the APIs of the bootloader's internals. The application communicates with the bootloader using a very thin API that's based on two C function calls. One is used to start an update, and the second is used to confirm successful boot after an update. wolfBoot uses the wolfCrypt crypto engine to perform signature verification using ECDSA, as we said. There is some architecture-specific boot code in the bottom layer, which is provided for the architectures we support at the moment, so ARM and RISC-V. And there is also a thin layer of target-specific hardware driver, which is only used to access the flash memory. And we do provide several examples for existing microcontroller from different manufacturers. The other abstraction is, in fact, a very thin layer that consists of these few functions that are used to lock, unlock, write, erase the specific programming flash for a specific microcontroller, and their implementation can be done either using a BSP driver provided by the manufacturer or directly accessing the registries as instructed in the data sheet. The target-specific code is hence very compact. The porting includes also creating a simple linker script, but it's, as I said, mostly focused on providing access to the flash memory. So it's about 6 MCU specific functions, which are normally implemented in 100 to 200 lines of code. And we do provide example code and example linker script for various platforms, NXP, Kinetis 6482, STM32, Microsoft Atmel R21, which is an Cortex M0, Texas Instrument CC26 series, and Nordic NRF 52. And of course, more are coming due to support to RISC-V. We'll soon release our first RISC-V platform implementation as well. There are generally two possible ways to implement firmware updates on a microcontroller. And this is a choice that had to be done when we designed wolfBoot. The problem here is that due to the physical memory mapping constraint on this kind of microcontrollers, a firmware image can only boot when it's placed at a specific address in flash, which is very well known at compile time and must be specified through the linker script. And so it is not possible to just boot any image from anywhere in the memory map. And the memory map is the corresponding to the physical location inside the programming flash. The two possible approaches here are clearly the A-B approach. So we have to know in advance if we are sending an update for partition A or B. So the partition of the primary programming flash is partitioned, is split into two partitions, A and B. And the firmware may run from any of them because there are always two versions of the same authenticated firmware. And the bootloader has to decide from which partition to boot. So the implementation of the bootloader in this case would be very simple, but on the other hand, that would be very difficult to deploy a solution based on this procedure, especially because the update server needs to know in advance which partition is available to transmit the update and only send to that particular device the image relative to that partition, so having the correct offset. Furthermore, this mechanism cannot be used with external devices that are not directly mapped in memory, because this mechanism expects that the microcontroller is able to run the code from both partitions at any time. The approach that we actually chose to implement is the boot update approach. So all the firmware images are always running from the same boot partition, so that has a fixed address in memory. The updates are always received on a second partition, which is the update partition. And the bootloader design is a little complicated by this, because we had to implement a swap mechanism that occurs when the update is validated after it's been received by the application. But this, of course, has the advantage of being much easier to deploy, because there only exists one version of a single version of the firmware that has been authenticated, and we don't have to ship two identical images except for the offset where it starts from, in order to receive the update on the target. And it's, of course, more flexible, because the update partition in our case can be mapped on a non-memory mapped device, so an external SPI flash, which gives the opportunity to use the whole programming flash for the current firmware that's being in use by the device. In the simplest case, so not using any external device, the programming flash of the microcontroller is divided into 4 partitions. The first partition is small and contains the bootloader itself. And the bootloader should be at the beginning of the flash executing space, because that's the default entry point for the first stage of our execution. The boot partition is the one containing the current executing firmware. The applications or the real-time operating system has to set its own entry point on the linker script accordingly, and but they know they will run always from a fixed position in flash, which is after the header in the boot partition, as we will see. The update partition is the same size of the boot partition, and the application will use this space to receive an update from a remote system. And at that point, the update will await to be validated and installed by the bootloader whenever valid into the boot partition. And there is also one small swap partition. It can be as small as the physical sector size on the flash, which is used only internally by the bootloader in order to provide fallback mechanism. So the 2 images are swapped in place. Using this swap mechanism, it is possible to validate that the update, it can actually succeed to boot on the device, and if something goes wrong, it allows us to roll back to a previous version, to the previous working version. So this picture actually shows a bit the state before and after the update. So on the top image, we see the bootloader and the first partition, the current firmware in the boot partition, and the new update that's being received by the application in the update partition, so the one in green. And after the update, the bootloader swaps the 2 images in place using the swap sector, and to roll back to the previous version in case something goes wrong with the version 2. It's just simply the bootloader rolls back by swapping back the version 1 where it was before the update was initiated. Now we have a quick look on how we manage keys, because that's a very important part on how the secure boot is deployed on real devices. So the key pair is generated once and stays, the private key is never shared, and it stays on the server. In fact, the security of this authentication process depends on the secrecy of this private key, which should be, if it's compromised, the whole boot mechanism is compromised. The public key is shipped with the bootloader. So we embed basically the public key in a buffer to be used by wolfBoot to validate the received updates. Of course, the public key is not a secret, so this does not pose any security risks, even if the public key is read out from the device itself. There is a sign tool that attaches a manifest header to the image. We will see more details about it. And the firmware version is also part of this signed payload. So it is not possible to alter the firmware version by manipulating the header. Let's see a bit how it works in practice. A Python script that's provided with the wolfBoot distribution is used to create this key pair that's used to sign and authenticate firmware updates. Private key is used to sign, and public key is used to verify. And then the next step is embedding the public key together with both boot sources to generate a wolfBoot image. This is done automatically by our makefile-based build system, which is, by the way, independent from the build system that you might be using for your firmware. So whenever we want to, whenever new firmware is available, the server may use the private key to sign it, and also in the process also associate a version number to it. This is done with the second Python script, which is the signing script, which is also distributed with wolfBoot, and it compiles this manifest header, which is fixed length, and puts it in front of the firmware image. This header also contains the SHA-2 digest of the firmware and the signature of the firmware itself. So the resulting file is this authenticated firmware that contains all this information, and wolfBoot can now verify the authenticity when the image is transferred to the remote device. For what concerns the application entry point, so in order to boot, the firmware image must take into account, as we said, the offset of this manifest header that's put in front of the firmware for the authentication. And so it means that the application has to be modified. Its entry point needs to be specified. This is done during the linking step of the application itself. This code shows how this is done if the application is based on a GCC toolchain using the linker script, but this is specific to the tool. In this case, we'll see that there is a partition dedicated for wolfBoot in the first 24K of the flash, and then after that, the image is of course not in scale. There is a header. That's the one that's being attached by the tool during the signing procedure. And so the image header, this picture shows a bit the content of the header that's put. Without giving too many details, there is this important signature field that contains the cryptographic proof that the image was signed by the appliance owner. You can have a valid signature only if you are the owner of the private key. So let's keep in mind that secure boot only solves one part of the problem because updates must be secured as well. This means that TLS or DTLS must always be used for firmware upgrades when possible, or at least it should provide some kind of encryption. Now, in the ideal world, if you're going for maximum security, your devices should also have certificates and keys to prove their identity before being able to download the firmware from the remote server. But this often requires secure elements. So there are several degrees of implementing secure boot. It depends also, of course, on the security design of the final product. But the secure boot solves the problems related to integrity and authenticity of the updates and implement the updates mechanism itself in a fail-safe way. But this is not a silver bullet. The application should still be using secure technologies and open standards to transfer the image. This is a clear recommendation for implementing secure firmware updates. Now, let's see an example of IoT product release cycle and how wolfBoot can be used to deploy IoT device with secure, authenticated and verified firmware updates. So we mentioned previously, the flash is initially divided into 4 partitions. When the device is in the factory, the JTAG can be used to upload the firmware. And the first thing we do, once the key pair has been generated, wolfBoot as the public key compiled in, and can be installed in its own partition. In the same way, we compile a firmware. We associate it to a version number, and we set its initial version, let's say version 1, and we install it in the boot partition. This is still part of the factory procedure, let's say. And of course, in the deploy server, we need the sign-in tool that's generating the factory firmware, which also need to be, of course, authenticated by wolfBoot. The authentication is done at every boot by wolfBoot. So the device like this is already ready for shipping. But from this moment on, we realize we don't need to access the flash through the JTAG anymore. So JTAG can be disabled, let's say, or there are mechanisms provided by manufacturer to activate some specific flash protection mechanism. So from this moment on, if we want the device to be shipped, this is the right moment to disable any access to JTAG to the programming flash. So this is how the device is going to look like the moment it leaves the factory. So on a normal day or normal operating condition, wolfBoot just verifies the integrity and the authenticity of the current firmware every time the device boots up. Of course, if we want to send the remote firmware update, we redo the same procedure. We associate a version number to the firmware, and through using the private key and the sign-in tool, we have a new version of the firmware that's signed, and it's ready to be transmitted to the device. The application will store the firmware received to the over-the-air procedure, and of course only the owner of the private key that's being created during the release can generate valid firmware update. And when the firmware upload is complete, wolfBoot is notified about the update, by the application, and it checks that the new image, first of all, if it's newer than the existing one, because since we know that also the firmware version is verified during this process, we don't want to allow rollback attacks, which would use well-known vulnerabilities to try and exploit our system. So the firmware update must always be newer than the current firmware for the update to begin. And of course, the second verification is that the integrity of the firmware is guaranteed, and this is done through the digest. And this is also done because since we are completely agnostic from the technology used to transfer the firmware update, we don't know if there might have been bit flipping or some kind of interference that would have resulted in a firmware update that's not valid because it has been corrupted. And the most important, we do verify the authenticity by verifying the digital signature that's provided in the header of the firmware itself, and corresponds to its unique SHA-256. So if the update verification is successful, we do swap the two images. So the firmware update is now copied in the first partition, and the previous firmware is temporarily stored in the update partition. If everything goes well at the next boot up, if the update can confirm itself by sending the success signal to the bootloader, the old firmware is deleted and the system can resume its normal operation. So the update partition is now ready to receive the next update. If something goes wrong though, as we explained before, the bootloader will notice that the application is still in a testing state, it's never been confirmed. And so it will restore the original firmware to put the device back in the state where it was before the update. So this is done basically by reversing the initial swap operation. And in either case, from the next boot up on, the system boots normally and it's ready to receive a new update, etc. This is the logic flow of the secure bootloader operation. So in a sunny day from the reset, there's no update available. The current firmware is not in an unconfirmed state. We verify the authentication and we stage the application. Only when an update is available, we do a certain number of verification steps, as we see, and this could lead to an update. And if the firmware is unconfirmed, the process is reversed by swapping the image back in place. Now, about the swap operations, we must add that on most platforms, these operations are completely fail-safe. So the power can be cut off, microcontroller can be reset at any time during the update process, including when the two images are being swapped by the bootloader in place. Because during the swap operation, wolfBoot keeps track of the completed step for each physical sector that's being copied. And there always exist two copies of the same sector during this interruptible swap process, which means that the swap is resumed if it's been interrupted during the previous run, which makes the swap operation completely fail-safe. However, this requires a specific feature that's present on most microcontrollers, which is the possibility to add zeros to the flash without erasing the entire sector. So what normally, how these flash memories work is that when you erase the sector, you can, the initial value is all ones, and you can only add zeros to write a specific value in a byte. But what happens is that on most architectures, it is possible to add zero bits to an existing byte, even if it's not the first time that this byte is being written. As long as we don't try to add ones, because this is physically impossible on these kind of devices. However, some microcontrollers don't allow this this kind of operation. We do have a workaround for this, but without this feature, it is impossible to guarantee that the fail-safe operation would be the swap operation, sorry, would be completely 100% fail-safe. And this is because we use the partition status flags that are some flags that we set at the end of each partition, which are used by the bootloader and by the application to keep track of the state of the partition themselves, and also of the single sectors during the swap operation. And this is done to keep status of what has been done in the previous boot across reboots and power failure episodes. We provide two digital signature algorithms. This is particularly important because by default, we provide this ED25519 digital signature authentication because this provides the an optimal code size, relatively small, with generally acceptable boot up times. But we do have a number of trade-offs in the code. So for instance, by using ECC256 curve, the boot time can be reduced significantly, but sometimes at the price of a slightly bigger bootloader code. And there are several levels of optimizations possible, which depend on the specific architecture in some cases, up until the point that ECC operation on some platforms can be completely offloaded to hardware components for maximum level of performance optimization. This chart here shows the trade-off between the bootloader code size, which is the columns in gray, and boot time in milliseconds, which is the orange line there. In three of the possible compile time configurations that we can set with wolfBoot. As you can see, the first column is related to the ED25519, where we get the smallest code size on this platform. It's about 20 kilobytes. The platform we use is Kinetis, NXP Kinetis K64. And with this algorithm, boot time is somewhere below 1 second in order to perform all the authentication of the current image in the sunny day case. Using ECC256, as you can see, even with assembly optimization on this microcontroller, reduces boot time to about 70 milliseconds. This is just by enabling single precision math Cortex-M assembly optimization. And as you can see, the cost is about 50% bigger code size for the bootloader in this case. Finally, when the programming flash is too small, as we said, to contain two partitions, we might want to use an external SPI flash. So one major advantage of our design choice for the updates is the possibility to have the update partition outside the addressable memory space. This is particularly important, of course, when you are able to add an external SPI flash to your design and still have secure updates without having to sacrifice half of the flash space to store the update that comes from the server. And of course, in this case, it's required to code 3 additional functions in your hardware abstraction layer to be able to implement read, write, and erase operation on the external memory. That might be an SPI flash device or anything else that can be addressable by the microcontroller. So, in conclusion, wolfSSL has the mission of bringing secure connectivity to any embedded devices. So it's the ideal security partner for IoT projects. But we learned that secure updates are important, not only to fix the defects that are spotted on the field, but it's also critical for vulnerability management if we want to play the same game that's played on big data servers and personal computers, because IoT market should be second to none on security management. And you should use wolfBoot because it saves time and effort and implements firmware authentication and a reliable update mechanism. And our specific focus is on delivering quality security solutions. So this concludes my presentation.
Thank you so much, Daniele. If you guys have additional questions, please don't hesitate to email them to facts, F-A-C-T-S, facts at wolfSSL.com. You can also get a hold of Daniele, Kristen, or myself. Our email addresses are below. Follow our blog. Stay tuned for additional upcoming webinars. And thank you all so much for joining us today. Daniele, thank you. David, thank you. Kristen, thank you guys.
Thank you, everyone.
Bye-bye.
Thanks. Bye-bye.